Hey class, Adam Ward here. Want to talk with you today about laminar flow in pipes. This is the first in a series of videos where we'll look at laminar flow, what it is, and what it looks like as an internal flow, meaning a flow inside of or constrained by some other object, like the walls of a pipe. All right, so learning objectives for today. You can pause the slide and read these to yourselves as you see fit. Okay, so laminar flow, this may not be a term you've ever heard of, or you may just think of water flowing as all the same. So we're going to differentiate two different kinds of flow in this class. For today's lecture, we're going to focus on laminar flow, and for the subsequent lecture, we'll focus on turbulent flow. So laminar flow is flow that is orderly. There is little to no mixing between streamlines. And its characteristic is that the Reynolds number of that flow is typically less than 2,100. So laminar flow, we think of, we want to think about all of these streamlines just sort of moving in an orderly fashion. There's no mixing in between them. It doesn't look bubbly. It doesn't look like there's this random or chaotic surface. It looks nice and smooth. And so just to remind you, Reynolds number less than 2,100, or rho VD over mu less than 2,100. In contrast, turbulent flow. And so turbulent flow is what you might think of when you see a river that is raging, where there are rapids. The water looks like it's boiling or bubbling. If you get the impression that you could put a drop of dye in there and that dye would rapidly mix and spread around, that's a good indication that you're looking at turbulent flow. Most of the flow you see in the natural environment is going to be in the turbulent flow regime, and that would be characterized by a Reynolds number of greater than 4,000. So the astute observer will notice there's a gap in between those. In between 2,100 and 4,000 for a Reynolds number, we would call that transitional flow, and that's not something that we're going to deal with much in this class. So to get an idea of what laminar and turbulent flow look like, actually, one of the best things that you can do is just head over to YouTube and type in laminar versus turbulent flow. There's a lot of great demonstrations out there. On our class website, I will have posted a video for you that I recorded from YouTube about laminar flow, where you can see a fluid get mixed and unmixed. So this would be the appropriate time to hit pause, go check out the flow that's doing a demonstration of laminar flow, and then come back to me here. So you are now back from having watched that visualization of laminar flows, if you are following along. And what you saw in that demonstration was that the effect of those no-slip boundary conditions in helping drag dye around in a circle and to be able to totally reverse it. Right? And that worked because there was no mixing of the flow. It was all that flow sort of stuck to a streamline rather than being mixed in between them. Okay, so one quick example here. Let's picture that we've got some industrial device here where we have yellow paint coming in from the top and blue paint coming in from the bottom. And those two are coming together into a 2-inch diameter pipe, and that pipe is 25 feet long. And so the question is, when this comes out the other end of the pipe, is it going to still be separated with blue flow on the bottom and yellow flow on the top, or will the two have mixed together and formed green? And so we're given some characteristics here about the fluid. The density of paint, its viscosity is 1,000 times greater than water. We've got a flow rate or a velocity of 4 feet per second, a 2-inch diameter pipe. And so the real crux of this problem is asking, is the flow laminar or turbulent? So if the flow is turbulent, we expect mixing and we expect green paint to come out. If the flow is laminar, then we expect those blue and yellow streaks of paint will stay in this orderly, organized fashion. They won't mix, and so they would remain separated. So the real question here then is about the Reynolds number, and do we have turbulent flow or laminar flow? So So just a reminder for us again, Reynolds number is fluid density rho times velocity v times the characteristic length scale. In this case, that's the diameter of the pipe d divided by mu, the viscosity of the fluid. And so we'll go ahead and plug in the information that we were given in the numerator. Density of the fluid, 4 feet per second for the velocity. And we had a 2-inch diameter pipe, and you'll notice I'm doing a unit conversion there to get it into feet, so my Reynolds number will indeed come out unitless. And 1,000 times the viscosity of water on the bottom, and that's what we were told the viscosity of paint was 1,000 times that of water. So we can plug that all into a calculator, and we end up with a Reynolds number of about 45.6. That is way less than 2,100, so no question that this is laminar flow. If it's laminar, those flow lines just proceed in parallel to one another. There's no turbulence that would cause mixing in between them. And so we expect 25 feet down the way, blue and yellow do not mix. We expect that paint to come out as still separated, not as mixed together into a green color. Okay. We're going to split our analysis then into which part of the flow are we talking about. And so this is a diagram out of the textbook that my class is using. You can see we've got this reservoir of fluid shown in pink. And the idea here is that you're looking at changes in the velocity profile as we move through the system. So when flow first enters this pipe, what I've circled in blue on the screen, it's nearly uniform in its velocity. So all of this flow is accelerating from being still and having velocity equals to 0 over in the reservoir. It's all being accelerated into the pipe. And so we start with this almost uniform fluid. What happens then is that no slip boundary condition at the pipe wall starts to propagate out toward the middle. So you'll remember from our early lectures in this class that that layer of fluid that's right up against the wall is in fact not moving. The wall causes that fluid to have a 0 velocity. And it's that first layer of fluid moving past it then where we start to get shear stress between a moving fluid and a non-moving fluid. And that shear stress is going to sort of propagate inward and cause this logarithmic velocity profile that we see. So we've got that no slip boundary condition that starts to cause that profile to develop. And we reach some point where we get what we would call fully developed flow. So this means that you've traveled down the pipe far enough that the no slip boundary condition and its impact have propagated inward, and we get that nice symmetrical logarithmic profile that we expect for flow through a pipe. And you can see that also in the bottom portion of the plot here again, where we get to what's called fully developed flow. Fully developed flow will be the subject of the next lecture that I record for you all to watch. So following onto this video, we'll look at fully developed flow. Anytime that we then perturb that flow, so for example, when we ask that flow to turn a corner, when we are accelerating or decelerating that flow, if there's a contraction or an expansion, we go out of being fully developed and we go into developing flow. We're not going to talk anymore about developing flow today, except to point out that this developing flow will get lumped into something that we ultimately call minor losses when we're dealing with turbulence. So tuck that one away in the back of your head for a lecture that is a few days from now if you are enrolled in my course. So we're first going to focus on the entrance effect. So what's happening in this region that says entrance flow region? How do we go from water that's not moving or fluid that's not moving to a fluid that is fully developed? So the length of that entrance region is something that we calculate as a function of Reynolds number. This is not something derived. This is something that's this is an empirical fit essentially. So the entrance length, or that distance to go from fluid not moving to fully developed flow, that is 0.06 times the Reynolds number if we have laminar flow. And that d is the pipe diameter. Right? So the entrance length relative to the pipe diameter is defined by 0.06 times Reynolds number. If you've got turbulent flow, you've got a very similar problem. It's 4.4 times the Reynolds number to the 1/6 power, or the 6th root of the Reynolds number, if you prefer it that way. So in both of these cases, we can describe that entrance length, and when we start to think about pressure drops, we'll be able to describe the loss associated with getting the fluid to its fully developed state, and then we'll treat that fully developed flow separately. So the reason we care about this is we're going to break problems down and say there's loss associated with the entrance and there's loss associated with the fully developed flow, and we can characterize or quantify those things. So as soon as we get beyond that entrance length, so when we've had at least LE of distance, our flow becomes fully developed. So how does this work? Let's do a quick example. So here's a zoom in on that same image. We're looking at the entrance flow region here and asking, hey, how long is it? And so if we've got a 1 meter diameter pipe, we've got 20 cubic meters per second flowing through it. How long do we think the entrance length is for this pipe? Now, before you continue to watch this, I would encourage that you hit pause. You ask yourself, hey, how am I going to find LE? What is my strategy going to be? So hit pause, lay out your strategy for yourself, and then come back with me and see how I did the problem. Okay, welcome back all. You should have a strategy in mind for solving this problem now. I'll show you mine. So we want to find this entrance length. And on the previous slide, we got two empirical versions of equations that we could use. One for laminar flow and one for turbulent flow. So if I want to use one of those equations, I've got to make that call. How do I know if it's laminar or if it's turbulent? And of course, you'll remember it's the Reynolds number. Find the Reynolds number, and I can decide, is it laminar or is it turbulent? How am I going to find Reynolds number? Well, I need fluid properties, I need velocity, and I need pipe diameter. And I look at that problem and I say, well, I've got the fluid properties. It's water. Those are things I could look up. I've got the pipe diameter of 1 meter. I'm missing the velocity of fluid, but I do remember that discharge Q is related to area times velocity. And so I could use that relationship to get the velocity, the average cross-sectional velocity of my water. So that's going to be my strategy. I'm going to work from Q equals AV, sort of backwards through my logic here to decide which equation to use and ultimately solve it. So let's do this. There's Q equals AV. I've rearranged it to solve for velocity. Average velocity is discharge over cross-sectional area, or 20 cubic meters per second, divided by, and the cross-sectional area for a circular pipe is pi over 4 times the diameter squared. Some of you will use pi times the radius squared. That's absolutely fine. You get the exact same answer. That the velocity here is just over 25 meters per second. Now I've got velocity. Now, before I proceed any farther, water moving 25 meters per second, that is an extremely fast flow. And so if I'm just sort of trying to develop a gut sense of what does it mean to be laminar or turbulent, flows that are fast are almost always turbulent. That V is in the numerator of Reynolds number, high velocity, high likelihood that we're going to get turbulent flow. So my gut says this is very fast and I'm expecting it to be turbulent. I think it's useful to write that down because if my conclusion is that this is laminar, not turbulent, I have sort of this gut check to say, did I expect it? Let me double check my math before I believe it. Okay, we've got velocity. Now let's calculate Reynolds number. Looking up, density of water is 999 kilograms per cubic meter. I'm plugging in the velocity we calculated, the diameter of 1 meter, and in the denominator, I've looked up the viscosity for water, 1.12 times 10 to the minus third Newton seconds per meter squared. Punch that in the calculator, cancel out units, and I get a Reynolds number of about 2.3 times 10 to the 7th. That is way bigger than 4,000. That means we have turbulent flow, and my gut was correct in this case. Now that we know it's turbulent flow, let's go ahead and pick the correct equation. Entrance length, LE, over pipe diameter D, equals 4.4 times the Reynolds number to the 1/6 power. And we can move that D to the right-hand side, so rearrange for what we're trying to solve for. Plug in our values. 1 meter multiplied by 4.4, that's from the equation, multiplied by our Reynolds number raised to the 1/6 power. And I calculate an entrance length in this problem of about 74 meters. Okay, so what we've talked about in this lecture is the definition of what laminar flow is. You should have watched a complimentary video from YouTube about exactly what laminar flow looks like to help you visualize that. And we've talked a little bit about this idea that flow takes some amount of distance to develop. In the next recording that I pull together for you all, we're going to derive the Hagen-Poiseuille equation, which is a description of fully developed laminar flow. So stick with me for that. I'll see you back here, and we will go through a derivation for how we deal with laminar flows in circular pipes. Thanks all.